Hello, welcome to another episode of the IFT ZK Call. Today, as always, Marvin Jones from Vac will give a talk about the polynomial commitments as the heart of the ZK protocols. So yeah, Marvin, stage is yours.
So thus far in our ZK call presentations, we've talked about polynomial commitments a bit. We've mentioned them in terms of zk-SNARKs when we did a brief crash course. And we also had dived into a lattice-based polynomial commitment scheme, which is interesting now that we're doing the introductions a few months later. But the goal of the calls have shifted a little bit. So let's make this concrete so that everyone knows what a polynomial commitment is. And to know what a polynomial commitment is, well, we really need to know what a commitment is. So we're going to start there. What is a commitment? Because polynomial, that's just a word tacked on to commit. But a commitment is basically, it's a compressed representation of data. The reason I'm putting compressed in quotes is because, well, I really didn't actually want to deal with the edge cases of like, okay, maybe it takes up a little bit more space if you have a small set of data, but it's a compressed representation. We're going to go with that. But more importantly, what it does is it binds the data. So if I give you a commitment to some piece of data, I cannot change that data and maintain that same commitment. That's the idea. And not only that, but if I gave you two commitments and I showed you the data that generated one of these commitments, you would look at and go, oh, you look at the two commitments and go, okay, any, mini, miny, mo, or flip a coin, you wouldn't be able to do better than a 50-50 guess. You don't have an actual insight into which one of those commitments the data is generated from. Now, that seems very vague, but we can make this concrete. We're all in Web3. We know what a hash function is. So if we think about the concatenation of a hash with some random piece of data R, and then the data we truly care about, well, a hash binds the data because, cryptographic hashes are collision resistant. So provided, we avoid collisions, which we should be able to, then that binds the data. You wouldn't be able to necessarily find another piece. And they also, have a nice preimage protection where if I give you the a hash of, if I give you a hash, you can't work backwards essentially. So that prevents this, maintains this hiding property. So when you think about commitments, and if you're not already familiar, this is kind of a nice simple example that you're probably more comfortable with, because again, a hash will bind it and hides it. I toss in the R mainly to make the fact that it hides the data if I give you the data outright in plain text more clear, because this just kind of illustrates that, yeah, if I have this piece of data, I could generate multiple commitments for the same data by changing this R, but I wouldn't be able to, find another one that easily find another one where if I change data to data one, that they would match, be equal. So that's the idea. All right. So now that we know what a commitment is, we can easily answer what is a polynomial commitment. It's a commitment, but for polynomials. And you're all thinking that is the worst way to define a polynomial commitment. But I'm not wrong. But it does have one additional step, because polynomials have a little bit more going on than just being data. you can evaluate polynomials. You can plug in a number to a polynomial. And what that would do is we would need to be able to prove these evaluations because, well, I've just made another claim using that data in that commitment. So you need to be able to verify it. So now that we go, okay, well, I should be able to prove evaluations. What does that even mean? All right, so if I have a polynomial commitment, that means that I have some compression C essentially, and that C is based on some secret polynomial, and it's publicly available. All right, not the secret polynomial, just the polynomial commitment is published somewhere that the verifier sees it, whether it's sent directly or it's on the network or something. And the verifier is going to query the prover for an evaluation. So that polynomial should be evaluated at V, so f of V. So the prover will provide Y, and Y is claimed to be the evaluation. So Y is claimed to be f of V, but we need a proof that Y is in fact f of V, and that proof is the really interesting thing because, yeah, we can claim things left and right, but why is it that is what we really care about. So before we get into techniques of how to do it, let's take a moment and go, okay, cool, I have the what, but why are we doing this? Why polynomials? Like, we're talking about computers. You can list things in computers as arrays. Polynomials are these weird algebraic things that I learned in high school or saw in bit in college whenever you saw them. Why am I making this more elaborate? Because we can just do arrays. Well, that's true, and arrays of numbers can be converted into polynomials. Just not going to dive into this portion, but the way that you convert an array into a polynomial it would be multilinear extensions, and that would be a polynomial with multiple variables. But that's not really within the scope. But again, if you want to dive deeper, multilinear polynomials, extensions. Okay. But you go, okay, well, that's more complicated because, again, array of numbers, that's a list. A polynomial, you have these coefficients, you have to have variable, that's weird. So why would I want a polynomial over an array? So we can see this with just this example. So I'm just going to be, oh, I see what I did. Okay. It'll make sense in a second. But the reason we want this is because if I have two arrays, I took one that had 6 elements, and I want to tell if they're distinct, I literally have to go through one at a time. Oh, there's a difference. And that could be quick or it could be slow. I mean, okay, when we're talking about 6 entries, yeah, that's going to be quick no matter what. But the difference could have been the first entry. The difference could have been the third entry. Or it could be at the very end of the list, as this example shows. So you have to go through the comparisons on each entry, to make sure that they match perfectly. And that takes big O of n. So what we can do instead is go, okay, if I want to show that two arrays are different, I could look at their polynomials that we just mentioned. And now the question becomes, how do you tell if two polynomials are different? Well, probabilistically, I could just do a single polynomial evaluation. Okay, you're probably going, what, on the previous slide, you didn't say anything about probability. We went through every entry. So why can't I just do a single query on the arrays and make that declaration? Well, if I pick a random one, I only have 1 in 6 chance of finding the entry. So that's a 1 in n for a general array to find the difference. But with a polynomial, you actually have more spots that you can check, because what happens is when you do these multilinear extensions, you've expanded the domain of your polynomial, of your array, to this polynomial. So you have an entire finite field. So you've increased the number of options that the verifier can check, but there's only d locations that those polynomials will match. The d locations, you can think about them as roots if you take the difference. I'll just say that and not dive any more. If you're curious about why it's d over the size of your field, that's a Schwarzschild lemma. So that's the probability of randomly selecting and finding the same value for these two polynomials. The difference, like identifying if two polynomials are different, the probability is almost 1. For d significantly smaller than the size of the field, which if you look at zk-SNARKs, you would see that fields are usually, I think, 2 to the 128, and you want d to be, well, a lot smaller than that. So this will be close to 1. So this is going to make it very easy with one query to tell versus this. So just out of curiosity, with how this would compare to our array example, because I have d in this expression for the polynomials and n for the array. D is approximately log n if you're doing multilinear extensions. Okay, everybody still good? I know I've just thrown a lot of information at you. I hear a question, but I can't see a question.
Yeah, thank you. You can ask.
Yeah, more of a maybe paraphrasing of that. Just want to make sure I understand correctly. So would it be fair to say that in a polynomial, like when we evaluate a polynomial, the end result of that evaluation kind of mixes in information about all the coefficients of that polynomial?
Absolutely.
So in that sense, we just have to compare one thing, which is the final evaluation. And if even one coefficient, any one of them is different, then with a very high probability, the result will be different. So it's
absolutely,
kind of,
yes.
Yeah.
Because the coefficients come from the array. So you're absolutely correct that what happens is essentially the polynomial is a mixing of these array entries. So any differences in the array will get amplified by the when we shift over to polynomials. Absolutely correct. Thank you. Any other questions or refinements? Anything's welcome.
So you heard another one? Oh, I didn't know.
Okay, I think Sergey's happy at the moment. All right, so
yeah, I just had to lower my hand manually. Thank you.
Okay.
Oh, okay. All right, so now that we know the what, the why, where are these used? Like, if we're talking about math stuff and theoretical stuff, where is it actually used? And I'm going to avoid the obvious pun. The answer is universal SNARKs. Sorry, I try avoiding puns as best as I can. So that's not a very informative answer. So let's expand on that a little bit. So a universal SNARK from our crash course basically allowed the same public parameters to be used on different arithmetic circuits. Just to be clear, if you're studying papers or anything about a particular universal SNARK, you're going to see that as a CRS, common reference string. If you're looking at non-universal ones like Pinocchio and Grot 16, their public parameters are structured reference strings. For the sake of sanity, I'm just calling things public parameters. but just for people who are not quite in the know. That's that. So Pinocchio and Grot 16, and if you're new to this, Grot 16 is probably the one you've heard of. If you attended the ZK call about the infinite inflation glitch from Zcash, that was based on an optimized version of Pinocchio. But both Pinocchio and Grot 16, those public parameters have to be generated on a per circuit basis, which is very annoying. It requires a trusted ceremony, a lot of volunteers to have people get the public parameters and know that there's not a trap door. So that's kind of unfortunate, but the reason you might care about a circuit specific one, again, briefly, is because those tend to be very efficient. So you would want to use those on circuits that are highly repeated. So for ZKVMs, you would use it for compression of outputs. For transactions that are highly repeated, you would use it on custom transaction circuits like Zcash would have used back when they were using Grot 16. More modern SNARKs are universal because you want to be able to just get your public parameters and use different circuits in different scenarios and not deal with these public parameters that have to be recomputed constantly. And the first one, I believe, is Sonic. Sonic was the first universal updatable SNARK, I believe. I apologize if I misspoke, but it came out very shortly before Plonk, which kind of supersedes it. And then you have Halo, which is based on Sonic, but all of these are universal. And universal SNARKs, because they are able to work with different arithmetic circuits, the details of the circuits cannot be baked into the protocol. With Grot 16, if you look at the circuit construction, is literally part of the public parameters. Instead, what Sonic and Plonk, and by extension Halo, would do is using universal SNARK design philosophy of being able to use different circuits, the public parameters need to be more general. And because of that, they have it set up so that you can essentially generate your polynomial commitments using these public parameters. And then those polynomials are essentially manipulated by the protocol. When I say the polynomials are, I of course mean the representation, the polynomial commitments are used in the protocol in very slick and clever ways so that it's general enough that it will work for any circuit that has a polynomial representation. Of course, I mean, they all do, but so you take the circuit, you get them into polynomial representations, and then you do black magic to it, we'll say. But that's the general idea, is that the polynomial commitments allow for these non-circuit specific designs. Okay. So now we're going to, go, okay, well, we know the yes.
I have a question here. Could you maybe clarify the relation between commitments being universal versus circuit specific, and the fact that Zcash is not Turing complete as a system compared to EVM based systems that are? Is it the same or similar notions of universality when we're talking about like currency based blockchains versus universal Turing complete blockchains, and how this map onto universal SNARKs versus circuit specific SNARKs?
Okay, I'm going to do my best. I'm going to probably ask for clarifications. I will repeat parts of it, and then ask for clarification. Sorry. Okay. So a universal snark, the only criteria there is that the snark, the public parameters for that snark can be reused in different circuits. So if you go back to sapling and sprout, I believe, and there might be another one, but I think sapling and sprout were both Pinocchio and Grot 16 for Zcash. If you go back to those were using Pinocchio and Grot 16 for transactions. The problem there is that you have to generate new public parameters if you want to do something different. With Zcash, I'm not actually sure why they want a universal snark, to be honest, with Zcash, because I mean Halo is cool and Halo 2 is cool, but I know with like Halo 2, part of it was that they were introducing recursion, and that recursion, the idea of using recursion was that they wanted to implement smart contracts. But to my knowledge, I think that's all been dropped because the Halo code base, last I saw, and this is from the Zcash's Discord, Daria Hopwood had commented that the code base that Zcash uses for Halo 2 would basically need to be rewritten to support recursion. This potentially is completely out of date, and like 2 days ago there might have been paper published. I apologize if I missed something, or but that's why I will say I think a year and a half ago. But in terms of why a turning a universal turning system, do I have that correct? Universal turning? Yes. You don't have to raise your hand. You can just interrupt me while I'm talking.
Oops, I was on mute. Sorry. Maybe clarifying my questions. Maybe I don't understand some very basic things. So, if you take Zcash as a just cryptocurrency system without smart contracts, basically the only thing that we're proving with each transaction that a transaction is correct, meaning that the balances all check out and like something sums to zero. Like I'm not generating money out of thin air, basically. Yes. And is it true that this fact leads us to being able to use non-universal snarks that are kind of fixed at this specific type of operation that we're approving with each transaction? Whereas more universal systems, the reason why they need universal snarks is because we're not actually sure what each next transaction is going to prove, because each next transaction can be some execution of a smart contract that we cannot predict the structure of.
Absolutely. The part that's weird to me, and maybe somebody that watches this video will comment and tell us, is that Zcash currently uses Halo 2, and Halo 2 is a universal snark based on Plonk. So after they got to Orchid, and I don't remember what the current update's name is, they swapped over to Halo and Halo 2. I apologize if I get the updates name timeline slightly off, but so that might be due to some convenience dealing with their shielded, de-shielded transactions as well, just to not have, but that part's currently escaping me. I'm kind of wishing I knew why. But yeah.
I think with Halo 2 you can batch proof and leverage that. I mean, if you have a lot of transactions, you can batch them. Maybe that's the feature there.
You can batch with Grot 16 though. It might not be as efficient though, because the efficiency of batching with Grot 16 is pretty abysmal. But at any rate, that's my suspicion though, is that If moving away from the Zcash example for a moment, just for sanity, because it has that oddity. Yes, if you were constructing a VM, a ZK VM, you would want to use something that's universal because you don't know what weird executions are going to occur. If you knew you were only ever going to do transactions, Grot 16 might be the way to go. I don't have a good reason why Zcash isn't using it at the moment, and I feel like I need to go look that up now, which is good. But yeah, so the moral of your question, I think I can answer. The specifics of Zcash, I don't think I can, if that helps. I'm going to hope that was sufficient.
Just maybe one more kind of follow-up or clarification. Again, please let me know if I misunderstand something. But my current understanding is that if we're developing a universal system based on some kind of VM, then every transaction, every execution trace basically can be unique in the general case and maps to a unique circuit. And then we are generating zero-knowledge proofs based on this particular circuit that was kind of derived from a particular execution trace. And this is basically what universality means here. Is it correct, more or less?
Yes, absolutely. I'm going to rephrase it slightly just for people who are not as familiar with ZKVMs as you are. But basically, the trace execution generates your arithmetic circuit, and that arithmetic circuit, like you said, is unique. So the ZKVM has no idea what weird black magic is getting that it's going to need to do to this arithmetic circuit. You just get the trace execution, it generates the circuit, and because of that flexibility in what it can be executing, it has to rely on a universal SNARK to generate it. Now, I will go one step further and say, okay, once you generate these proofs, some ZK VMs, such as RISC-0 and Nexus, will do a compression layer, because once you have your proof, you know whether it's a SNARK, Plonk, whatever, you apply essentially a Grot 16 circuit that takes in a universal SNARK of a particular design, and then you can apply, you have a fixed circuit then, and you can compress it. So, but within the ZKVM execution itself, that first step where you don't know what that trace is going to be, that's where you definitely need a universal SNARK. So hopefully that confirmed that you have the right thoughts in mind and translate it for people who are not as familiar.
Yep, thank you.
Okay, fantastic. Okay. That was actually a wonderful pause, by the way, because I know from someone observing, you're like, well, you're halfway through your slides and we're getting really technical things. Now we get to take a step back and do less technical things. So if you had to have your mind blown by strange questions, we're going to actually now look at a fairly straightforward example of a PCS. We're in Web3. We've seen Merkle trees left and right. And if you've not seen Merkle tree, don't worry, there'll be a diagram on the next slide. But what we're going to do is we're going to take a polynomial with some degree D and a finite field. Why a finite field? For this example, you really don't need it to be a finite field. It could be any finite set. My polynomial for Merkle trees doesn't have to be a univariate polynomial, but it's going to make talking about it a little bit easier. So, but the idea is that with a Merkle tree, I have a bunch of leaves. I'm going to identify each leaf with a particular number in my field. And then what I'm going to store in that leaf is going to be the hash of the evaluation, for that corresponds to that leaf. And then we construct that Merkle tree. We get the, by taking all the hashes, and we get the root hash. That root hash is my polynomial commitment. Okay. And then you go, if you can visualize that, you go, okay, I have a polynomial commitment. How do I prove an evaluation? Well, we're going to do that using usual Merkle proofs. But again, just in case you're not as familiar with Merkle trees, the idea is I'm going to plug into this layer right here as I accidentally highlight everything that I'm moving the mouse over. Those are technically my leaves. So I'm taking these evaluations, hashing them, and then H00 is going to be a leaf, H001 is a leaf. This is just kind of there for thinking purposes. And then the hash of two siblings give us this one, and then we kind of work our way up taking concatenations. Now, if I told you, if you queried V4 and you go, okay, well, what is f of V4? And I gave you the number. Well, I need to do more than just give you the number because, well, this is, we like decentralized systems. You don't like trusting me. So I need to convince you using this polynomial commitment, the root hash, that f of V4 is correct. So I give you this value, and I have to give you the path. So if you have f of V4, you can take the hash and find H110. So I'm going to give you H101. This is the neighbor. And you can concatenate these and get H10. So I need to give you the next value on the list, which is H11, which you then take both of these two and you can compute the hash and get H1. And then I had to provide you H0, which again, you take the hash of both of those. And if that matches the root hash that I had published earlier, you go, oh, FV4 was the correct evaluation. So a Merkle tree can be treated as a polynomial commitment. All right. Now I will, since I mentioned finite fields, I will make the offhand comment of, someone might be going, well, finite fields that we usually consider are prime order, and you have 8 entries. I felt that if I left this portion off, it would just look funky. So just get over it. I needed a placeholder there, just to make the Merkle tree look nice. But anyway, the next thought is like, okay, well, that's relatively nice. We like Merkle trees. That proof of evaluation makes sense. Why don't we just only use Merkle proofs for this? Well, there's 2 really good reasons to not use them. And yeah, they're used sometimes, but in general, like there's 2 good reasons not to do it for everything. And one is that the prover has to evaluate f at every point in that given domain, in our case, the whole finite field, because that domain is where the verifier is going to query. And that domain also affects the probability of it being valid. So you kind of want the domain to be large, which then means the prover has to do more work. Not only does the prover have to do more work, but that makes the tree bigger, which means I have to provide you with more values. So the verifier has to do more work too. And then the really big reason is that hash functions do not support homomorphic properties, which means, maybe I would like to add things, or maybe I would like to multiply things. So it makes arithmetic very unfortunate because you can't do it using the hash functions. So that's basically why we don't do it. But I think Merkle trees make a fairly nice example, especially after the conversation we just had. So, everybody's hopefully back and nice and calm. All right. Let's have a brief digression into Pedersen commitments. All right. So we have a finite field of size of order P and a group of prime order P. And we're going to do a Pedersen commitment. And a Pedersen commitment will just compress a vector of numbers in F to a single group element. So to do this, we need a list of group elements. These are fixed. These will be like used for anytime I want to generate a commitment. So if I want to commit to these numbers, I will just take V1 times G1 and just add it to V2 and so on. I just do this, and that's a fairly nice compression, just of using additive groups. So that's nice. But the next question that you might have is, well, do G1 through Gn, do those elements matter how we get them? Yeah, they really do. So if I have a relationship that I know, say G2 is equal to TG1, I can do some fiddling with my known commitment. So I honestly produce this commitment. I can do some fiddling to find a commitment that has the same commitment. I can find another vector that has the same commitment. Specifically, I changed the first entry and I changed the second entry. The problem with that is that it violates binding. So, So to avoid violating binding, we need to make sure that we get these group elements in a manner that we know how they're generated, and we know that there was no funny business. So if you look at there's a paper that describes like hash the curves that will tell you how to generate these. That's actually how Bulletproofs claims to be to have a trustless setup, is that they are able to generate from a hash to a curve so that these elements are chosen randomly. Other ways might involve I think beacon is a ceremony that will also produce these. And with KZG, we will see that we'll mention that you can do this with power tau ceremonies. So lots of ways you can get them. But KZG, by the way, it's just the abbreviation of the author's names. So if you're wondering if it stood for something crazy math-wise, no, it's actually the most straightforward naming convention in all of ZK. It's just the author's names. Okay. So what KZG is at a very high level is it's a Pedersen commitment on the coefficients of the polynomial. So if I have a polynomial, then I will just pair A0, the constant coefficient, with G0, and I just do this pairing throughout all of these values. And that's great. Now, with KZG, we need to have a little bit more with our group elements other than that they were just generated with no known relationship. I need that GI is actually equal to alpha I times G. G is just some generator. It really just G0, to be honest. But if all the GIs are like that, then I have a relationship. I know how these generators relate to each other. That's not good. But to get around that, we need a trusted setup. And what that trusted setup will do with power tau and so on is that you can use it to generate these values in such a way that alpha is never known to anybody. In particularly, what happens is that alpha is generated in a multi-party computation, and as long as you have one honest user in that computation, alpha can never be known. So that's great. I will put the caveat: it never can be known. We're assuming quantum computers don't exist that can break just the discrete log problem of the appropriate size. So, given that, we have our generators, our public parameters. Okay, cool. So I can't shift the values like I did in Pedersen commitment. Okay. And we know how to get a commitment. So the next question is, how do we do a proof of evaluation? And what KZG does, and just for clarity, if you're looking at the number of slides going, oh, Marvin's not going to tell us, the full math detail. You're correct. I'm going to give you a good picture of how to do it. So if you're reading the paper, you have the idea in your head of why they're doing stuff. But what the evaluation does is it uses very clever use of basic algebra. When I say basic algebra, I mean literally high school polynomial arithmetic stuff, polynomial division. And then it uses elliptic curve pairings. Okay, that part might not have been in high school. That's the moon math portion. But the rough idea is that what we'll do is, for an evaluation point, I have x minus v. So you're going to ask me to evaluate the polynomial at v. Well, this will perfectly, monomial, not monomial, whatever. My brain's broken on math terms today. F minus v, though, will divide f of x minus f of v, though. That's the key, is that because this will perfectly divide it, there's some polynomial q of x times that multiplies to f minus v that will give us, this perfectly. And what we will do now is the prover will commit q of x. So again, you've queried the evaluation point at v. The prover is going to give you this f of v, and they're going to give you a commitment to q of x. They will also need to give you a q of v as well. I didn't write that, but yeah, they'll need to give you that. But once you have that, we essentially have these commitments. We have our commitment for f. We have our commitment for q. And if you're wondering why it's d minus 1, it's because the exponents will add. So if this is d minus 1, this is just 1. When you add d minus 1 to 1, you get d, which we need to get because the degree of f is d. And we can also go so far as to compute the commitment for this univariate polynomial x minus v. Now, why we care about those commitments is because once we do, these commitments are what we essentially have. I don't have q of x given to me in plain text. I don't have f of x given to me in plain text. So I need to be able to do the arithmetic on these polynomials using these commitments. But Pedersen, which these 3 commitments are all Pedersen commitments, are only additively homomorphic, which means, yeah, I can add these like if I take c plus d, then yeah, I get direct addition on the coefficients. But I would like to actually multiply like d times e so that I have, something like c, and then, I can use the fv portion somewhere. So why we use elliptic curve pairings, if you're, again, go read the KZG paper, is because the pairings will allow us to do the multiplication that we want to do based on this portion right here. Because what KZG is actually doing, if you look at the elliptic curve, very briefly, if you look at the elliptic curve identity, is that it's doing essentially f of x times equal to q of x times x minus v plus f of v. I believe f of v is over there in the identity. So that's what's happening, is that they're using, again, high school algebra in a very clever way and pairing it with elliptic curve pairings. All right, so that's, again, the very rough idea. And, this should be more than enough for people who want to know vaguely how KZG work. Hopefully, if you know how, have seen KZG and looked at it, hopefully this actually solidifies it better. And if you're wanting to dive deeper into it, this is hopefully going to give you a really good start when you start seeing all the black magic moon math occur. Anyway, that's all I have. Any questions? I hear an unmuted mic, but I don't hear a question.
I think there's no question yet. Thank you for this presentation. Maybe since the KZG uses some, they said toxic waste, like
yeah, the alpha
pre-calculated stuff, right? And it makes it very it makes it very very succinct. You know, the SNARKs is actually succinct proofs, and the succinctness comes from the feature of the KZG, right?
KZG doesn't prevent succinctness, but I think I don't think you can fully credit succinctness to the polynomial commitments themselves, because Grot 16 and Pinocchio are, of course, succinct without KZG. I think that KZG, crediting KZG essentially succinctness to the reason Sonic or Plonk are succinct really undersells some of the amazing stuff that those protocols have in their design. I think it's more that KZG can be used to support succinctness, but I fully believe that if we sat down and we wanted to make a very terrible protocol, we could use KZG as a basis, and it would be exponential.
Yeah.
So I just wanted to say that. But it does enable succinctness. It doesn't prevent it. We'll say it that way.
Yeah, but by the way, the KZG is not the post-quantum secure, right? Because it depends on the problem.
Absolutely. KZG is not the. I thought about including slides on the Halo polynomial commitment scheme that's based on the product argument from bulletproofs, but that would actually be a little bit harder to explain in this high-level view, but that's also not post-quantum secure. To be honest, most of ZK is not post-quantum secure. Of course, you have stuff like Plonky that uses FRI, and those are post-quantum secure. Let me clarify. Those are plausibly post-quantum secure. And you do have some more modern polynomial commitment schemes that are lattice-based, and those are, again, plausibly post-quantum secure. So there is somewhat of a shift to get away from some of these polynomial commitment schemes, but when the danger of quantum computers occur is still to be determined, to my knowledge. But yes, you're absolutely correct that the discrete log problem is reliant here. Specifically, you can see that with G1, because G1 alpha.
You can extract it.
Yeah, immediately. You get alpha immediately. Now it is worth noting that even though it's not post-quantum secure, it is still forward secure if you have a hiding element. Is that true?
Yeah.
Yes. So if you have a hiding element, and I'm not even sure if that's fully necessary, to be honest, but it is anything that was previously encrypted committed to won't be insecure, but It's just the insecurity that arises is the fact that a malicious prover can then produce whatever commitment and violate binding. Binding does not get violated.
And a quick reminder: we have also the previous episode about the lattice-based post-quantum secure polynomial commitments named Greyhound. You can find in the same channel, and it's also polynomial quantum computer secure. So it's based on lattices, and yeah, it's very new according to the KZG or something, right? This
Yes.
is one of the state-of-the-art PCS.
I believe that all the lattice-based ones are basically within the last like 2-3 years. KZG is from 2010, which hurts me a little bit to say it's classic, but you know, such is life. I mean, to be honest, at this point, you could say Plonk is a classic zk-SNARK. And it's only 5-6 years old. But so much has been built off of it that I could see it being called a classic proof at this point.
Yeah. Do you have some questions? I think no. Thank you, Marvin, for this nice presentation. I think we see that how the polynomials are important and makes very smooth the computations. And yeah, see you in the next episode. Thank you for watching.